Okay, so we begin with turbulence. The contents of this lecture would be, what is turbulence? First we have to understand that. Then we come to the state that why it is necessary to study turbulence. Then the next article would be, what is the problem in solving turbulence? And finally, what are the available solutions? So in nutshell, what we are saying is that what is actually turbulence? Is it necessary for us to study turbulence, or we can escape it? Right? Then if it is necessary for us to study turbulence, then what is the problem in solving it? Because we will find that turbulence has a typical problem and it cannot be handled the way we can handle other problems. And for that reason we have to make certain assumptions, approximations. Okay? So in a way there is no direct solution of turbulence available to us. Then if we are not able to solve turbulence just like other differential equations, then what are the available solutions to us? How do we go about solving it? So this is what we are going to study. Now, first example of turbulence is this. You can see here, if you see a candle which is extinguished, there is a lot of smoke is coming up. Okay, the smoke, and you see that as far as the smoke is up to this red line, it is following that there is a pattern. It is slightly shaky because of the air, you can say, and subsequent particles are following the preceding particle. There is a pattern. But moment we come across this point, the red line, you find that there is a disturbance. Disturbance starts growing, and then these particles, smoke particles, they start moving in random direction. Okay. So initially the flow is laminar, but after some time it becomes turbulent. Now why does it become turbulent? We will talk about it. That there are forces which are responsible for laminar flow, there are forces which are responsible for turbulent flow. Now if the forces responsible for turbulent flow are more, then it will become turbulent flow. And if the forces responsible for laminar flow are more, it will be a laminar flow. It actually depends upon the Reynolds number. Okay. So we take another example. This is the case of, you can see that in the beginning, from where the smoke is coming or the gas is coming in, there is a sort of a pattern, although still there is no pattern. Randomness is there, but still the flow is contained. But as it passes on in the gas chamber, there is a lot of mixing is there. Okay. After that you cannot say anything about the flow. So from, you can say, initially from the laminar flow, or you can say translaminar flow, it is becoming turbulent flow. This is what is happening. You take this as the example, another flow, in which you find that these circular motions are being generated and they follow a pattern, right? They are following a pattern, but slowly they are increasing, and down the line they will break up and create turbulence. Here you see a pattern. So whenever you are able to see a pattern, this is not turbulent flow. Okay, of course the cause of generation is this, you can say, cylinder where the flow is getting detached and some sort of oscillation it has picking up, which is creating those circular motions, but later on it becomes a, so you can see here the generation of, you can say, circular worlds which are being generated here. Okay, so what is actually turbulence? Now how do we define a turbulence? In a turbulent flow, velocities along with all other properties. So what is turbulence? So in turbulent flow what happens is velocities along with all other properties. So you have a flow which has not only velocity, there are many other properties also there, of a parcel of fluid. Now what is a parcel? Parcel is actually a drop or a group of molecules. Okay. Now, so what happens that they are moving randomly, and with time they are changing. So this is, here we are showing u as the velocity, but it could be any other property. In fact, all the properties would change. It's not that only one property would change, the rest all will remain same. So they vary in a random and chaotic way. Then the fluid is considered as random, turbulent. Okay, turbulent flow. Now, then how does this turbulence originate? From where does it start? So there are three sources. First is the free source, a free surface. You have a free surface which is the source. Now what happens is, if you look a surface, there is a air here and liquid here, there is a change in surface. Now what happens if the molecule is inside liquid? This molecule is surrounded by so many molecules around it. So they do not allow it to leave its place. Still it can move, but it's something like that you are in a crowd. It's heavily, you can say, heavy crowd is there. You can't change your path much, especially when you go to temples. You are not free to move. You just follow the flow, how the people are going. You can't go left, you can't go right. There's a push which you get from the back and you keep on moving ahead. Right? But if you are close to the open space, right, there is a tendency to escape because you are free from the one side. On one side you are bound because you cannot go back, but on the other side you can simply escape. So this is the place where you actually disturbance is created. Right? So long you are in the midst, in the center of the fluid, inside the fluid, occupied by the same type of fluid around you, you cannot move arbitrarily. The moment you are on surface, you are free and you can move out. So this is how the disturbance is created. The free surface of liquid, at the free surface the molecules of the liquid are bound only on the one side, hence they are relatively free to move out of the surface. Any disturbance at the surface may lead to independent and random motions of some parcel of the fluid. Once you leave the fluid, then you follow your own trajectory, right? तो ये जो है, कई बार आपने देखा भी होगा मंदिर में दोनों साइड बार्स लगी हुई हैं, तो क्या करते हैं, बार में से साइड से नीचे से निकल जाते हैं और फिर कोई दूसरा रास्ता ढूंढ के अपना निकाल के वो सेंक्टम सेंक्टोरम में पहुंच जाते हैं आप, क्योंकि आपको पता है मंदिर बंद होने वाला है, अब यहाँ 1 घंटा खड़ा रहना पड़ेगा, तो देयर इज़ अ वे आउट. So you can move independently. So this is what happens, and that part is random. Once you leave the surface, you leave the boundary, you can move the way you want. Okay. Of course, these particles are not conscious, so still there are forces, but now the forces are less, and they follow a random trajectory. Then surface roughness is also responsible sometimes for the turbulence. Now, if you look at surface in a detailed way, enlarge it, the surface is like this. Whatever the surface you see is not that smooth. There are ridges and the valleys there. Okay. Now, when the liquid comes or the gas, whatever the fluid comes and hits it, it gets deflected. Right? It gets deflected from here. But the deflection is not much. If the speed is low, right, you can ride over the rough surface. Again, you take a practical example. If the road is bad, what do you do? Slow. You move slowly. You follow the contour. And you don't go much off the road. But if the road is uneven, quite uneven, and you are going fast, what will happen? You will be thrown out. Something comes, you are at a high velocity, same thing, you going on a road, some obstruction is there, some stone is there, some blockade is there. If you are at a slow speed, bumper is the example. The bumper comes, you slow it up, just glide over it and go away. So if your velocity is slow, you can glide over it and go. But if the velocity is high, what will happen? You'll jump. So this is what is happening here. You are jumping. So it depends upon the velocity. If your velocity is less, it is a laminar flow. If the velocity is high, it becomes a turbulent flow. Once you jump from the bump, where you will land is not known. Right? So the same thing happens here. These particles come, hit, and then they go randomly wherever. Because now they are not in the control, because nothing around to control them. Okay. So surface roughness leads to turbulence. Then you have another thing. If there is a sudden change in the boundaries, okay, then also turbulence is created, randomness comes in. Again, take the example of a crowd. There is a narrow passage through which you are going, and then comes the big, you can say, the ground or veranda. Take the example of temple again. If you're passing through a small passage you will be very ordered because there is no way you can escape from there. The moment you enter that open space, then you start running in different directions. So now you are free. So same thing happens here. The moment you are, so long you are here, you are bound here. The moment you land up here, you find an open space, you adjust yourself, move out. Okay. That is a conscious movement where you do it willingly. Okay. Seeing that there is no disturbance on this side, you follow it. But unconsciously for material thing, there is no restraint there, and the small disturbance present in the molecules or perturbation present, they become free to move. Okay, that is what, because perturbations are always there. Some perturbation, some random motion, some molecular motion is there, right? The moment you find that there is no bounding forces, you escape. So this is also the reason for turbulence. Okay. So when a disturbance is amplified and sustains itself, right? Sometimes a disturbance is created and it dies out. Okay? Disturbance will always be there. But if it sustains itself, it is amplified and sustains itself, it leads to turbulence. But it can also die out. So it's not necessary the flow will always remain turbulent. It can die out also. Even if there is a tendency to go random, it may actually not go. What happens is, you look at this. Now, there is something called Reynolds number, and this Reynolds number is represented as inertia force divided by viscous force. Actually, we write it as rho u L by mu. Okay. Now, this is inertia force. Why it is inertia force? It's basically representing, rho is representing mass per unit volume, u is the velocity, and L is the characteristic linear dimension. It is telling you about the kinetic energy, right? And because it is in momentum per unit area, it is basically, you can say, momentum per unit area. So it's inertia force and then divided by viscous force, right? This is what is Reynolds number. Mu is the dynamic viscosity and nu is kinematic viscosity. The units are given, you can see. Now what happens at low Reynolds numbers? Inertia forces are small than the viscous forces. If Reynolds number is less, the numerator is smaller, denominator is more. Okay. So as a result, what is happening? The naturally occurring disturbance don't grow and dissipate on the way, and the flow remains laminar. Right? So however, at higher Reynolds number, inertia force dominates, it sustains, amplifies the disturbance and leads to turbulence. Now, so it is basically this Reynolds number which determines that what will be, whether the turbulence will be there or it will not be there. Okay, and how do I give the example to you that viscous forces and viscous forces, you know that it is there in the liquids, of course it is there in the gases also. You can see that suppose I drop water on this, or on the other side I have a fluid which is viscous, maybe honey or maybe oil or something else I drop. Now you can see the spread. The moment the water will fall, it will spread like anything, right, all around. But your honey or your oil or even something more thicker than that, it will remain there for a long time. It will be slow to spread, and by that time you can collect it. So why it is happening is because in what is viscosity? Viscosity is actually, there are two molecules here, right, and they are bound to each other. More this force, more is the viscosity. If this force is more, viscosity is more. Okay. So what is happening that these molecules are tied together. Now when you give a motion to velocity to any one of them, if this force is more, right, this will not go far, right? It's something like that. If your springs, you can assume that the balls are these balls are tied with a spring, and you can imagine that even there is a spring here, right? You have a spring like this. Now you hit it. The disturbance will be smaller if the spring force is more. Okay, if it is less, then the disturbance will be more. And it may happen that if the velocity is very high, this particle may leave this place and come here, because these are not threads, like these are you can say bonds of field. Electric field is there, the bond is there. So it will just escape from there. Or you take the example of you can, ये जैसे आपका ये आप देख लीजिए, इस तरह का एक वो है, और यहाँ पर एक बॉल है, इसको आप वेलोसिटी दीजिए, ठीक है, ये डिपेंडिंग ऑन द वेलोसिटी इट विल गो अप एंड कम बैक, बट आफ्टर सम टाइम if the velocity is more, you can still increase the velocity. ये यहाँ से जो है निकल के बाहर चली जाएगी. तो ये जो इसका बाउंडिंग है, ये जो लिमिट है, एक लिमिट तक ये जो है आप डिस्टर्बेंस थोड़ा बहुत देते हैं वो वापस आ जाता है, ठीक है ना. उसके बाद वो जो है डिस्टर्बेंस इतना ज़्यादा है कि वो जो बॉन्ड है वो परमानेंटली ब्रेक हो जाता है. वाई द बॉन्ड इज देयर? बिकॉज टू पार्टिकल्स आर टुगेदर, दैट इज वाई द बॉन्ड इज देयर. इनवर्स स्क्वायर होता है ना, फोर्स जो होती है, दैट इलेक्ट्रोस्टैटिक फोर्स, दैट इज इनवर्स स्क्वायर ऑफ द डिस्टेंस. सो एज यू गो अप अवे, योर this force reduces. Same thing happens in the when you launch a satellite, if your velocity is not enough, you will come back. You throw a ball, it will come back. The rocket goes up, it will come back. You require an escape velocity. What happens that? That bond is permanently broken and it leaves and goes away. So the same thing happens here. And more the strength of the bond, more velocity you require. Right? So if mu is more, your Reynolds number is less. Now to increase the turbulence, to bring out the turbulence, you have to increase the velocity. So this is what you will have to do. So this is what I was saying, that you look at the Reynolds number, that now it is clear that two particles are joined together by a bond. There is a force between them, that is the electrical force. As they go away from each other, that force reduces. Now if you have a more velocity, more disturbance, it can go to a farther place. It goes to a farther place and the bond is broken, and then it becomes free, just like escape velocity. So, and once it is free from that, then the random motion is produced, the turbulence is produced. So what happens is, your so if you have this some flow is going like here, all right, you have a something is flowing like this, right? A particle escapes from here, and because it has velocity, it comes here and then it is free to go anywhere. So that is how the random motion is created. Now, what are the properties of turbulent flow? Turbulent flows are highly unsteady. Unsteady means they are changing with time. Okay, they are three-dimensional in nature, which means that instantaneous velocity varies with time rapidly in all the spatial dimensions. So it's truly random. The moment the particle is free from there, it's a regular path from the laminar flow, it goes anywhere and in all the direction it has velocity, and they are changing very rapidly. Okay, then they contain a great deal of vorticity in the vortex stretching is one of the principal mechanism by which the intensity of the turbulence is increased. Now we will talk about this. What is the vorticity? They have a vorticity because when these particles leave the place, they actually have rotational motion also. And you know, conservation of angular momentum, that's the principle is there. So it maintains that vorticity. Okay, it has to, and it will take time to die out. Right? A simple same thing, just like you have a particle which is moving, and what happens? Its velocity is there, but as the forces, resistance forces act on it, slowly it loses the velocity until it takes up the velocity of the surrounding. Same thing happens with the rotational motion. It has to preserve its angular momentum, but because of viscous forces, those forces come on play on it, and it may slowly die out. And you can see when you in the some rivers or ponds, you can say there is a vortex motion you can see. Even your tornadoes and this cyclones, The vortex motion is there, and that is the real danger, because it sustains itself because of angular momentum. Okay, so now then there is another thing happens, that in turbulence, parcels of fluid with differing concentration of any conserved property are brought in contact and churned together. Now, when they have left their place, right, they are going to land somewhere else. Now, they had the properties from where they started, right? Normally what will happen, you are having uniform flow, the properties are not much changing, or they are changing slowly. But if you move one particle from one place, right, if suppose you are here, you pick up one particle from here and put it here, what will happen? When the particle lands on the other place, its properties are different, quite different, right? So then what will happen, the final mixing, this mixing जो यहाँ पर, इसका यहाँ mixing होता है फिर, because the moment there are property difference in properties, a differential is created and the mixing. Suppose a hot particle from here lands here, which is a cold area, heat transfer will start. Suppose this has a parcel of carbon dioxide, a bubble of carbon dioxide, it goes here where there is a oxygen. What will happen? That carbon dioxide will start spreading, right? Or a smoke from here, आप ब्लास्ट करते हो ना वो क्रैकर्स, वो स्मोक जाता है दूसरी जगह जाके, वो धीरे 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 फिर वो जो है, यहाँ से आपने स्मोक फेंका या जो भी है वो दूसरी जगह जाके लैंड किया, यहाँ पे कंसंट्रेशन था उसका, और वहाँ जाके लैंड किया और वहाँ जाके वो। तो ये जो मिक्सिंग है, मिक्सिंग, इसमें दो तरह की मिक्सिंग होती है. वन इज कॉल्ड टर्बुलेंट मिक्सिंग एंड द अदर इज कॉल्ड मॉलिक्यूलर मिक्सिंग. ठीक है. नाउ इफ द फ्लो इज लैमिनर, turbulent mixing will not take place because it's not a turbulent flow. So yeah, we have two types of mixing. One is called turbulent mixing, the other is called diffusion mixing and turbulent. Now you see that this is a drop, right? Or we can say parcel of a fluid, a group of molecules of a fluid. Now if it is following the diffusion process, it comes here, you see that this thickness of this wall is growing. This is diffusion. Slowly and slowly its color is changing, its constituent is changing, its properties are changing, right? And as it, because what is happening on this side, there is a fluid which has a property different. So the particle is having properties, let us say majority is red here and you have blue here, and that what happens, slowly and slowly that red starts reducing, the blue starts taking it up and diffuses. But if it is turbulent, what happens? This particle comes here and it breaks, right? And then it starts mixing at many places. तो एक मिक्सिंग आपकी ऐसे है कि यहाँ पे जैसे मान लीजिए आपका इधर है, अगर आप एक आपका ये फ्लोर है, ठीक है, let us say देयर आर टू डिफरेंट थिंग, टू कलर्ड जो है क्या कहते हैं। तो मिक्सिंग कैसे होगी, यहाँ से ये मिक्सिंग होगी। डिफ्यूजन होगा धीरे धीरे। आप देख सकते हैं वो इंक का एक एक्सपेरिमेंट होता है, वो you can put ink in and slowly that color will get diffused and finally the whole liquid will become of same color. Same thing is about the smoke also. You have a smoke source here, from here, slowly and slowly initially you are seeing, suppose आपने यहाँ पे smoke का वो छोड़ दिया कोई, तो धीरे धीरे वो फैलता जाएगा slowly and slowly it will take the, and on the other side you have a fan rotating here, ठीक है, इसमें जो है you put a fan here, then what will happen, ये बहुत जल्दी से कलर मिक्स हो जाएगा. You can do it with your hand also. You can put a tablet of a color at the bottom of the glass and leave it. Slowly and slowly it will leave the color, and वो जो मिक्सिंग होगी आपने यहाँ पे वो लग दिया, क्या कहते हैं, ठीक है, और ये थोड़ा सा धीरे धीरे ये मिक्सिंग होती जाएगी, and finally you will find that after some time it will mix up. The other thing is you start churning it, वो जल्दी मिक्स हो जाएगा, तो वो टर्बुलेंट मिक्सिंग है. In turbulent what is happening is, because the particle is moving from its place to another place, right, and there is a, then it mixes up here. तो मिक्सिंग एक एंड से दूसरे एंड तक वो मिक्सिंग हो रही है, जबकि अभी जो है एक एंड से. इसको और कोई एग्जांपल हम ले सकते हैं कि सपोज यू हैव अ सम हॉट, this is block is lying here, right, you leave it here in the air, slowly and slowly heat will go away and it will start cooling. But you can do what you can do, you can put fan here. What the fan is doing actually, fan is creating turbulence. Now what fan is doing is, it is bringing this air here, it is bringing this air here, cold air, and then taking this away. So now what is happening, the parcels of the fluid are coming, they are taking away heat and going away. So एक है यहाँ पे slowly and slowly, यहीं पे जो है वो धीरे धीरे एक से दूसरा, दूसरे से तीसरा, तीसरे से चौथा वो हीटिंग हो रही है. और एक जो है बल्क ऑफ, मतलब इवन आई वुड से दैट मिक्सिंग में मॉलिक्यूलर मिक्सिंग जो है आपकी, यू कैन ऑल्सो टेक इट लाइक दैट, मॉलिक्यूलर मिक्सिंग में मॉलिक्यूल्स मूव एंड मिक्स. And in turbulent flow, because when it is a laminar flow, there is a no movement of parcels within the fluid. Parcel is what? A group of molecules, maybe 1,000 molecules, 10,000 molecules together. They form a drop and they move from one place to another place. Now, if it is not a turbulent flow, what is happening? There is no such movement of the bulk parcels. The movement is in terms of molecules only. So the molecules are small They're very, very small compared to the parcel. So they will carry a small thing, small heat, small velocity, small, you can say, properties from one place to another place. Slowly and slowly they will move. But when it is a parcel, then what happens? 1,000, 10,000 molecules together jump from one place to another place. And there they have a lot of velocity, they start mixing up there. So this ball comes here, breaks up, and so this mixing will be very fast. So in return, what happens in turbulent flows, your mixing is very, very fast. This is what we were saying. The mixing is, the final mixing is, so final mixing is by diffusion, because these particles, when they come here, they start diffusing. And finally you will find it becomes all uniform. Okay. So, which is enhanced many a times due to turbulence. So this mixing is enhanced. So in a turbulent flow, mixing becomes very, and that is why you will find that in turbulent, when you talk about heat transfer, you talk of increasing the turbulence so that you can increase the heat transfer. Okay. So this is what this. Okay. Then there is something called vortex stretching we were talking about. Vortex stretching is like, you can say that there is something called energy cascades in turbulence. These, you are saying these vortices, these are the vortices which are here. Now these vortices break and more smaller vortices are created. So it's like this, you have a vortex here, motion here. Due to the surrounding flow, it gets extended, it's moving like this. It is further extended like this, becomes a long, and then it separates into two. And then, so these vortices, this is called cascading. Bigger vortices move, they break into smaller, and then they keep on passing on. Right? So vortex stretching also takes place. This is how the turbulence moves. Right? Because if there is only one this vortex, it will follow one path. Now it breaks into two, so it is going in two different paths. Then you have 2 to 4, then there are 4 different paths. So that disturbance actually keeps on, you can say, multiplying and takes over the whole thing. Right? So normally vortex will be created from one particular source, because you have to generate vortex in a way. In a particular motion also the vortex is created. That you saw when we were talking about this diagram, where the types of turbulence or the different diagrams showing turbulence. There was one in which you were seeing that the vortices were formed and they were moving ahead. Third one. Now then they enlarge as they move. They are stretched and then they break into two and then they keep on going. But they are created at a particular place because of a particular structure there. Okay. Somehow the turbulence is created. You could have noticed that somewhere you find, when you look at a river and some stones are in the river, you must have seen a particular point the water starts rotating. And there is a pattern there. Because the shape of the stone is fixed, the flow of the water is fixed, and you get a particular pattern there. But then afterwards it becomes all mixed up, right? So the mixing of parcel of the fluid having different velocities while momentum remains conserved, the total kinetic energy of the ensemble reduces. Now what will happen? That the momentum will remain conserved. That because for momentum to go, you have to have a forces on the boundary. Okay, internal forces cannot do away with the momentum, but your kinetic energy goes away. The kinetic energy loss gets converted into thermal energy due to viscosity, and you can see the example of these balls. When they hit each other, what happens? The momentum remains conserved, the kinetic energy reduces, because there is always a loss of energy. If it's explosion, the energy can increase, but if it's not an explosion, when two balls mixes, then what happens? They maintain their momentum, but kinetic energy is lost. Okay, there it is lost because of collision, here it is lost because of mixing. Okay, so this mixing is a dissipative process. The lost energy is irreversibly converted into internal energy of the fluid. So this also happens in a turbulence. You get momentum remains conserved, but your kinetic energy keeps on reducing. Okay. Now then, this mixing is a dissipative process we have talked about, and the energy is converted. Now both mixing and heat transfer increase by order of magnitude due to turbulence. What I am saying is that when there is a turbulent motion, mixing, that is diffusion process, or two different types of fluid mixing with each other, and heat transfer, both increases by order of magnitude as compared to normal flow, which is a laminar flow. If the flow is turbulent, the heat transfer increases many times, and your mixing also increases many times, right? So what I am saying is that we had the second question, that can we escape turbulent flow? The answer lies here, that we cannot escape turbulent flow, because the behavior of turbulent flow is much different from the laminar flow. So you cannot actually understand turbulent flow using laminar flow. You have to study it differently, and that is why we have a laminar flow and study of turbulent flow separately. So then, and there is another reason, that normally the flows are turbulent. So two things are happening, that the flows are normally turbulent, right? Turbulent comes in very easily. And the second is, the behavior of turbulent flow is much different from laminar flow. Therefore, you have no escape. If you want to study a problem, you have to study it as a turbulent flow. And if you don't want to study the turbulent flow, you are not studying the real life problems. So it's no use. Because in life, when you are actually using engineering to apply it, the problems are going to be mostly turbulent flow. So from laminar flow, if you want to use the laminar flow and extend it to the turbulent flow, you will not be able to do, because their behavior are different. And The problems, if you think that okay, we will leave the problems of turbulent flow, then it is also not possible, because most of the problems of real life are turbulent flow. So you have to study, there is no escape from it. Okay. So from here onward we will move on to the issue that why we are not able to solve the turbulent flow. Okay. We'll stop here.